Alright, so in this video, we're going to go through a more formal teaching of how to calculate what's called an empirical formula. We're going to learn how to go through and in the lab and on paper, how to calculate the formula for various things. This is one of these things that if you've done it for a little while, this is kind of second nature, and it's kind of easy once you understand the concept. But when you're learning it, sometimes the concept isn't very easy. When I was in high school, this is one of the things that I just had a real big mental block about. I didn't understand the basic idea of what the reasoning behind why you did what you did was. The other time in my life that happened was in integral calculus, and I still don't understand some of the reasons why you apply some of the methods you do in integral calculus. But this I finally figured out after doing this a number of times. I'm like, okay, duh, this makes some sense now. So I'm going to try to make you understand the whys. I'm going to show you the hows, and the hows aren't going to make any sense until you actually start doing them. And once you start doing the process over and over again, hopefully the what you're doing and how you're doing it is going to start making enough sense that it'll just naturally flow. So what's an empirical formula? Well, an empirical formula that we can calculate is the simplest whole number ratio of atoms in a compound. So let's say I have a compound like C2H6. Well, that's a molecular compound. It has 2 carbons and 6 hydrogens. And if we want the empirical formula, you reduce the subscript. So you divide everything by 2. So the empirical formula for this C2H6 compound, the simplest whole number ratio is CH3. Now, that doesn't make a lot of sense for a covalent compound because you understand that a covalent compound naturally exists as C2H6. When you're calculating empirical formulas, it's kind of cool because for ionic compounds, there's no difference between the two. When you're calculating molecular formulas for covalent compounds, then there's an extra step added on here in a little bit. The gist of what you're going to do is based on the idea of this formula. You know that there's 2 carbons and 6 hydrogens, but the conceptual wall that you need to climb over is that this also means moles. That for every 2 moles of carbon, you need 6 moles of hydrogen to make this particular compound. And what we're going to end up doing is we're going to be calculating the number of moles. And that's easy to do because we have a relationship between mass and moles of a substance. So that's ultimately what we're doing is we're calculating moles, and we're comparing moles of one to moles of the other. You're saying, okay, if I have 1 mole of this, how many moles of this do I make? That is how you're going to make your formula. All right, so let me put up the hows. Here's how you're going to make the calculations. This may not make a lot of sense to you until we start to apply it. And we're going to apply it to 3 problems here in the notes. I have one more problem that is not in the notes, another example of how to calculate this that I will link to in the description or here at the end of the video, depending on how I figure out how to do what. So a lot of the problems are going to start off by telling you a percentage of a compound, a percentage of an element in a compound. Something like this compound is 30% lithium and 70% bromine. What does that mean? Well, that means, for in terms of mass, if I had 100 grams of it, 30 grams of it is lithium and 70 grams of it is bromine. And so step 1 is if you're given percentages, just assume you have 100 grams of the compound, and those percentages just become masses, 30 grams of lithium and 70 grams of bromine. Now, steps 2 and 3 are the main things that you're going to do. You're going to convert those into moles now. 30 grams of lithium, convert that to moles. 70 grams of bromine, convert that to moles. And in step 3, you divide by the smallest number of moles. You're setting that equal to 1. When you divide by the smallest number, you'll see that in just a little bit. And you'll see a mole ratio. For every 1 mole of this, you have how many moles of this other stuff. Now, sometimes when you get done with step 3, you have a fractional number, like 2.5. And you'll see that in our first example. Well, if you have that, then you have to multiply by an integer. And I said here in number 4, you multiply by integers 2, 3, or 4 to get whole numbers. You are probably never going to multiply by 4. I've never seen any problem where you have to multiply by 4. That would be mind-boggling to me. 3 maybe. Not sure if I've seen that or not. I want to say yes, but I can't quite remember. 2s, you multiply by 2 all the time. You almost always double it. So let's take a look at their problem. Let's actually get in here to the nitty-gritty of what we're doing. Typical problem. Here you have a compound, 25.9% nitrogen, 74.1% oxygen. Find the empirical formula. The first thing you do is assume you have 100 grams. If I do that, then that means the percentages just become grams. I have 25.9 grams of nitrogen and 74.1 grams of oxygen. And if you're watching this, I highly recommend you get yourself a calculator and you play this along with everybody. Check my numbers, check my math, and all that particular good stuff. So step number 2 then is once you have your grams, you're going to convert all of those into moles. And so you're going to set up a mole conversion here. You've got 25.9 grams of nitrogen, grams to the bottom, moles are on top. What number always goes with moles? Milton Union students, 1. And now you find the molar mass of your nitrogen, which is on the periodic table, 14.01. And on pencil and paper, you can just call that 14. It's not going to be a big difference here. All right, so I've already calculated here on the calculator, and here's my calculation. If I take 25.9 divided by 14.01, you get 1.8486, etc. Well, I gave that out to 4 decimal. I'm sorry, this one I only gave out to 2 decimal places, 1.85 moles. Do the same thing now with nitrogen. I said nitrogen, I meant oxygen. Do the same thing for oxygen. Convert that into moles. So grams to the bottom, moles on top, and the mass of oxygen is 16, and you end up getting about 4.63, which is the other number I had on my calculator. Here it is, 4.63 or so. All right? Okay, so step 2 is done. Step 3, you're going to divide by the smallest number of moles. And so the smallest number of moles is nitrogen, 1.85. So you're going to divide everything by 1.85. Well, what you're doing is you're setting nitrogen equal to 1. For every 1 mole of nitrogen, how many oxygens do you need? And when you do this, you should get about 2.5. Now, it's not going to be exact. I'll show you the calculation here on the calculator. It comes to about 2.505. Okay, we're going to round these off to more reasonable numbers. We're just going to call it 2.5. Well, you have your formula right now. It's N1O2.5. But, of course, you can't have 2.5 of an oxygen atom. You can either have 2 or you have 3. This is where step 4 comes into play sometimes. In this case, we're going to multiply all the subscripts by 2. So you multiply N1 by 2 and you get N2. You multiply O by 2 and you get 5. So the formula, the empirical formula, the simplest whole number of ratios, is that for every 2 nitrogens, we need 5 oxygens. What we don't know is really what the actual molecule is at this point in time. If this was an ionic compound, we'd be done, because ionic compounds don't exist as molecules. They're in these big crystal lattices that you've seen in my class a lot. So this molecule could actually be N4O10, or it could be N6O15. We need one more piece of data. That'll be in a follow-up video. All right. Let's take a look at a couple more problems here. So this one has 3 atoms in it, 3 elements. We have sodium, sulfur, and oxygen. And I'm not going to show you the calculations on these, but you should play along and use your calculator and pause every once in a while and calculate these things. So like on 1 and 2, you should say, okay, the masses are given, so convert the moles. Well, do this and don't show it to yourself until you've done it. And check your answer. You're allowed to pause this at any point in time, and I highly recommend you do when you're first learning it. So our first conversion of sodium grams into sodium moles is set up right here. And again, if you round that off to 23 at the bottom of the parentheses here, that's okay. That's not going to change this number much. I will tell you that you should take out your moles to several decimal places. I'm doing 4. Don't apply rules of sig figs here, because the rules of sig figs are going to cause you to round too steeply at first. Always tell people, if you do sig figs, you apply the sig figs at the end, not in the middle of your problem. All right, so converting sodium into moles, we have this many moles of sodium. We're going to do the same thing for sulfur. Again, this number is from the periodic table. It's just the atomic weight. And you get this number of moles of sodium, 0.0792. You do the same thing for oxygen. You get 0.2381. What's step 3? Step 3, you're going to divide by the lowest number of moles. And so the lowest number of moles is this sulfur right here. So we're going to divide all of these numbers by the number of sulfur moles we have. So that's our next step. So we do sodium divided by the number of moles of sulfur. We do sulfur divided by the number of moles of sulfur. What you're doing is you're setting this equal to 1. So for every 1 mole of sulfur, I need 2 moles of sodium. Or for every 1 atom of sulfur, I need 2 atoms of sodium. Finally, we have to do it with oxygen, and so we do our division, and we get 3 oxygens, or about. It's rounded. If you're playing along and trying to do it, you'll find out that it's not quite that. You got to round it off pretty well. I'm rounding off to 1. I'm being, I'm doing what I want to do here to prove the point. So what's our formula? Well, for every 2 sodium atoms, I need 1 sulfur atom and 3 oxygen atoms. It didn't come out to be a half of any atom. We don't have to multiply by 2. So step 4, we don't even have to apply. Our formula is Na2SO3. Which you'll learn how to, you should recognize that. You should be like, oh, that's sodium sulfite. Piece of cake. All right, let's take a look at another one. In this particular one, this is given percentages. And we have carbon, hydrogen, and nitrogen. You assume 100 grams. The percents are now masses. Convert into moles. This should say moles, not grams. Moles, not grams. I can't really mark up on this right here, but that should say moles, not grams. All right, so let's convert grams into moles. And so here's the carbon calculation. And here is the calculation for hydrogen. You got about 16 moles or so. 1 divided by, you're basically having the same number because the mass of hydrogen is 1. And then finally we have to do nitrogen. And so nitrogen comes out to be about 3.2 moles or so. So now, you'll notice, by the way, nitrogen and carbon are very, very close. They're very similar numbers. So step 2 is done. We're converted to moles. Step 3, you divide by the lowest number of moles. And the lowest number of moles, just barely, is nitrogen, 3.2191. So that's what we're going to do. We're going to divide everything by the lowest number of moles. So carbon comes out to be about 1. And nitrogen comes out to be about 1. Hydrogen, once you've done that, comes out to be about 5. All of these numbers are fairly close to whole numbers. And so our formula is CH5N. I don't have to multiply by integer. It didn't come out to be 5.5 or 1.5 on any of these. It came out to be 1 to 5. All right. Hopefully these examples have shown you how to set up and calculate. If you're in my class, you can now work on parts of the homework packet. We'll be setting up and preparing for a lab next week where you're actually going to determine the formula in the classroom. We're going to be doing that by taking some magnesium and we're going to expose it to oxygen. And we're going to find a compound and we're going to actually find out what the formula for that is. All right. If you have any questions, you can get a hold of me in class through the usual methods. Thank you for your attention.